Problem 4, week 4. This is a problem where you finally get to make some application of your understanding of forces and moments to a real building construction problem. So this is a beam, and this is the way you'll see it diagrammed in these types of analyses. On one end, this beam is on a pivot, and so essentially this pivot you can think of as being like a hinge that this beam can pivot up and down on. On the other end, the beam is on a roller, and that means that the weight of the beam will come down and sit on top of the roller, and the roller is allowed to move left and right. And the result of that is that you're not able to develop any leftward or rightward force on this end of the beam. It's not particularly critical to this problem, but it will matter when we start getting into more complex structures where you're going to need to be able to figure out, can a particular component produce a certain type of reaction. Now, the first part of analysis of this structure is to get this uniformly distributed 180 pound per foot load into a single vector. And if you look, this load is distributed from a distance 9 feet from pivot point A all the way out to 18 feet from pivot point A. Well, one of the principles we can use is that if the load is uniformly distributed, we can think of it as acting in one location right at the center with its full quantity. This is kind of the center of gravity assumption, that you can treat something as though all of its mass is at one point. So there's one vector right here that is 4.5 feet plus 9 feet, so this is 13.5 feet from point A, because it's right in the center of that second 9-foot interval. Now, the force there is going to be equivalent to 180 pounds per square feet times the span of 9 feet. So 180 times 9 is 1,620 pounds. So one 1,620 pound weight at this location is equivalent to that 180 pounds per square foot, or per foot distributed over the entire 9 feet. Now, if you think about the sum of all of the forces in the y direction, this problem does not ask you to calculate reactions, but let's just think about all of the forces in the y direction. That's going to be important later on. Sum of forces in the y direction, well, that's 900 downward, so we'd call it negative, 6,300 downward, and 1,620 downward. If we add these three quantities together, we get 8,820 pounds, which agrees with the answer that is given in the key to this problem. The sum of the forces in the x direction, well, I don't see any arrows pointing left or right, so there are no forces in the x direction. Now, moments. Let's think about the sum of the moments. So you could solve this problem a couple of different ways, but the way that they've given the answer is in reference to the location of point A. So we're going to look at moments about point A. So I'm going to say sigma m sub A. It just means the sum of the moments about point A. Well, what moment does this 900 pound force create? Recall that torques or moments are calculated by the force times the distance from the pivot perpendicular to the force. So if you look, this force is exactly in line with point A. It doesn't generate any moment at all. So that term is 0. The 6,300 pound force is acting at a distance of 9 feet. So the moment generated by that will be 6,300 times 9. Which is 56,700 foot-pounds. And the moment generated by this this one single 1,620 pound vector is that force times the distance of 13.5 feet. So 1,620 times 13.5, and again the 13.5 we arrived at because 9 feet plus 4.5 feet, half of this other 9 gives you 13.5. That generates a moment of 21,870 foot-pounds. And the problem does not ask for reactions. Understand, though, that if this is to be in static equilibrium, what we'd have to find is a counteracting moment equal to this sum and a counteracting series of forces equal to the sum of the y forces. So in this case, let's calculate the total moments about point A. It's going to equal the sum of that 56,700 plus 21,870. So the total moment, 78,570 foot-pounds. Now what the problem asks for is an equivalent system that generates the same downward force and the same moment. So let's think about what we know. What it's asking for is basically a single force acting at some distance that we need to solve for. So I'll label this with a question mark. And what do we know about the sum of the forces in the system? There has to be a downward force of 8,820 pounds. So this force has to be 8,820 because it's asked us to resolve all of these into one single force. And the moment's got to equal 78,570. Well, if the moment about A equals force times distance, then it's simply this force, this 8,820 times the distance that this question mark refers to. And we know that that product is equal to the moment, which is 78,570. So how do you get d by itself? Well, you divide both sides by that 8,820. So 78,570 over 8820. And let's use our calculator. Results in about 8.91 feet, which agrees with the answer as given in the answer key. So 8.91 feet. This distance here, again, if we were to label it in the drawing, 8.91 feet. So what does that mean? Well, that means that all of this complexity together, this 900-pound vector, this 6,300-pound vector, and then this distributed 180-pound per foot load can be simplified down to a single force of 8,820 pounds at a distance just shy of 9 feet, about 8.91 feet from the pivot point. This is the type of the analysis that pretty much every other static problem is going to involve, which is trying to take complex pictures and just simplify them down into simpler representations so that we can get numbers.